Hello, everyone. Today, I just want to quickly provide you guys with a review of null hypothesis significance testing. I know that many of you had questions and concerns and felt that you still had a lot of issues associated with null hypothesis significance testing. So I hope that with today or with this review that I'm going to do for you, hopefully it'll answer a lot of your questions for you. Okay, so let's begin with the following. I think one of the biggest issues that we all kind of encountered in terms of null hypothesis significance testing in terms of this week was the following. When is it that I'm supposed to use null hypothesis significance testing? I think that's a major question that all of us had. In the past weeks, we've all seen how we use the mean, median, mode, standard deviation, variance, range, etc. So we've all seen the application for the use of our stats. And now we kind of come across this theoretical issue of, well, I'm testing my statistic for significance, but what am I really testing on? What is it really used for? So let's think of the following situation. When we as researchers, because remember, statistics are going to answer questions that we have, right? So we're going to answer research questions. So let's say, for instance, I pose a research question. What's my research question going to be? Let's say that my research question is going to be the following. Is there a difference? So is there a difference between individuals, oh, there we go, individuals who receive a treatment, whatever our treatment may be, so let's say for instance a drug that we're going to give people, in comparison to individuals who do not receive a treatment, okay? Now, in this week, we've been talking about our z-score, or our chapter covers the issue of z-score, and it really covers the issue of a one sample z-score, which is essentially here what we're going to be talking about. So our one sample z-score. And our one sample z-score is essentially saying the following. We're going to compare my average for my group, right? So for instance, we're going to look at my treatment group, and we're going to compare my value to a population average that's already been given to us by previous research, and then we're going to divide that difference divided by our standard error, right? So in our particular case, let's say for instance we know from previous research that individuals who don't receive a treatment on a specific type of disorder, let's say for instance that they're going to display in terms of the number, so the number of symptoms associated with their disorder, let's say that they display an average for a population equal to 80. Okay, so they display in a 24-hour period. So here I'll say in a 24-hour period, they display about 80 symptoms as an average. So we find this in the population, right? So let's say that previous research has been doing research on this issue, and they find that for the population of individuals who have a specific disorder, whatever disorder it may be, it doesn't really matter, they display about 80, an average of 80 symptoms in a 24-hour period. So now what we've done is we've created a treatment, and we're saying, okay, now we want to compare to see my group. So in other words, I have now used a treatment, right? So here we have no treatment in this particular case. And now I give them a treatment, right? So I've randomly selected individuals from the population, and now what I'm doing is I'm giving them a specific drug to see if now the symptoms of, let's say for instance, depression decrease from 80 to something else, or do they increase with this specific treatment within that 24-hour period. So here I'm dealing with the population parameter of mu. Here I have my sample mean. Okay, so let's say for instance, we now identify that with my group, 75 is the average of the number of symptoms that are displayed in a 24-hour period based with this treatment. Okay, so in other words, when I give them my drug, individuals display roughly about 75 symptoms associated with depression, in contrast to the population when they don't have any drugs in their system, they display about 80 symptoms of depression. So in other words, I have this question that says, is there a difference between individuals who receive a drug in comparison to individuals who do not receive a drug? So from research questions, we're going to build a research hypothesis. Okay, now remember from my lecture, I said that there's this clear difference between a research hypothesis and the alternative hypothesis and the null hypothesis. The null and the alternative hypothesis, so H0 and H1, these refer to the population, and we're going to talk about these in just a second here. But my research hypothesis is essentially what it is that the previous research has been telling me about this specific issue associated with my research question. So in other words, other researchers have been doing research associated with how it is that different treatments or different drugs may potentially affect individuals with depression. So it may reduce, it may increase, it may not change their symptom levels. So in other words, let's say that previous research has said that if you give individuals a specific type of drug, nothing happens to them. So I predict, based on previous researchers' work, that I say that there is no difference between the drug treatment group, so the drug group, and the no treatment group from the population. Okay? So in other words, there's not going to be a difference between these two groups. So that's what I'm predicting. Why am I predicting that? Because let's just say, for instance, that that's what the previous research has said. Is that really what they say? I don't know. I'm just making that up. In this particular case, is just an example for our purposes. So in our particular case, that's what we're predicting, that we're saying that there's not going to be a difference between my group's average and the population average. Okay, that's essentially what we're saying here, that there's not going to be this difference between the drug group and the non-treatment group. So in other words, the non-drug group, in terms of my average and the population average. Okay, that's essentially what we're saying here. Now, out there in the real world, okay, so we have to think about the population. Out there in the real world, when we're dealing with the population, there's two possibilities that may exist. So think about like flipping a coin. If you grab a coin, there are two possibilities that may exist. There's going to be heads and there's also going to be tails. So think about in the real world, as we're doing research, we're flipping this coin. And when we're flipping the coin, it's either going to land on heads or it's going to land on tails. In our particular case, we're thinking about the null and the alternative hypothesis. So out there in the real world, there's this possibility that the groups are not going to differ, right? So that's one of the possibilities that exist out there in the real world, that the groups do not differ. So in other words, no difference or no effect. Okay? The other possibility that may exist out there in the real world is that the groups may differ, or that there is going to be a difference, or that there is an effect. That's the alternative. So there is a difference, or there is an effect. Okay, so those are my two possibilities, and these are the only possibilities that may exist out there in the real world. So if I'm doing research and I'm trying to look at how a treatment, such as a drug, may potentially affect an individual or a group of individuals who have, for instance, depression in our particular case, there's two possibilities. Number one, the drug is not going to change them. It's not going to have any effect in terms of their scores in comparison to the non-drug group. Or there is going to be this difference between the groups in terms of the drug and the non-drug group. Okay, so those are the possibilities that may potentially exist. Now, in your textbooks for this particular discussion, our textbook talks about the one sample z-score. So essentially what the one sample z-score is saying is, look, I've calculated, or I have a group of individuals who I've given the drug to, and I've calculated their average. Their average is a value of a 75. And I know what the population average is. How do I know what the population average is? A group of researchers have been doing previous research on this specific type of population, and they've tested everyone, and when no treatment is given to them, this is the number of average of symptoms that are displayed in a 24-hour period by people who have depression. Okay? So we have, for my drug treatment group, we have 75 symptoms that are displayed in a 24-hour period, and I know that in the population, 80 symptoms are displayed. So this is the formula that our textbook is using for the one sample z-score. I know that this formula is different than the z-score formula that we've been typically working with. That was the score minus the mean divided by standard deviation, or the score minus the population average divided by sigma, the population standard deviation. But essentially, this formula is still very, very similar to that. Now, essentially, what we're saying is, look, I'm trying to compare my average from my group to the population average and identify to see if the two groups differ. So in other words, I calculated for my group an average of a 75. The population average is an 80. So now I have to come to a decision if my drug is actually having an effect on my individuals with depression. So in other words, is it significantly reducing the symptoms of depression or is it not? So in other words, do people who receive a drug who suffer from depression better themselves, or does the drug actually help them in any capacity in comparison to individuals who do not receive any treatment at all? That's really the question here that we're trying to answer, which is this question here. So is there a difference between individuals who receive a drug or who do not receive this drug in terms of the number of depression symptoms that they display in a 24-hour period? So now you'll notice here that our value of a 75 and our value of an 80 are not the same value. So you may look at this and you may say, well, hey, you know what? You are actually decreasing the number of symptoms that individuals suffer from in comparison to the population. So yeah, your drug is working. But here my question is this a significant difference? And that's a major issue that we have to concern ourselves with. That term, right? So that aspect of significant. So is this difference significant or not? So in other words, is the difference between a 75 and an 80 extreme or not? If it is extreme, we have to then come to a decision about the null. If it's not extreme, we have to come to a decision about the null and also about the alternative. Now, remember that when we were dealing with the null hypothesis, when we introduced the null, we introduced this idea that the null always says no difference, no effect. So here, essentially, when we look at this one sample z-score or one sample z-test that we're using in terms of the textbook, the null hypothesis for the one sample z-test would predict the following. The average for your group minus the average for the population is equal to 0. So in other words, your group average, no matter what the treatment is, minus the population average, the ones who don't receive the treatment, their difference between the two would be equal to 0. So thus, your z-score would be equal to 0 in this particular case. Okay? The alternative hypothesis predicts that your group average is not going to be equal to the population average, so thus the difference between the two are not going to be equal to 0, or that z is not equal to 0. Okay? So now you'll notice here the clear difference between the two. The null is telling me, look, between the two groups, the groups should not differ. The score should be equal to each other, thus the difference should be equal to 0. So thus z would be equal to 0, because if you notice, this portion here that I've just written out for you is the numerator of the formula right here. So if that numerator is 0, thus z would be equal to 0. The alternative is telling me, look, the difference between your average and the population average is not going to be equal to 0, so thus z is not going to be equal to 0. So here we can also write this out as the following. My group average, let me go ahead and fix that really quick. There you go. My group average minus the population average are going to be equal to each other, thus the difference between the two are going to be equal to 0. And the alternative would say my group average is not equal to the population average, which is not equal to 0 in this particular case. Okay? So here, this is the way that we would symbolically write out our null and alternative hypothesis in our particular case for our one sample z-test. So here, in other words, my average minus the population average is going to be equal to 0, z is equal to 0, or my group average is going to be equal to the alternative it's going to be equal to the population average, which is equal to 0. Or the alternative hypothesis would predict that there is going to be a difference between the groups. There is an effect. So thus, my average minus the population average is not going to be equal to 0. Z is not equal to 0. Or you can say my group average is not equal to the population average, which is not equal to 0. So ultimately here, what are we trying to do? We are trying to do the following. We're trying to decide if the difference between a 75 and an 80 is extreme. That's what we're trying to conclude about. So essentially, we're trying to say if the difference between 75 to 80 is extreme, we're then going to reject the null hypothesis that the two values are equal to each other or that they do not differ. And we're going to try to say that the groups do differ. So in other words, my average minus the population average is not equal to 0, so thus there is a difference. But here we have to come to this decision too, that we have to think to ourselves, okay, if somebody tells me that they got an 80 on the exam and I got a 79 on the exam, does that mean that they are significantly smarter than me? The answer would be no. Why would the answer be no in this particular case? Well, more than likely, them differing by 1 point may potentially be due to error variance or just due to pure random chance. So here, in our particular case, that's what we're trying to decide here. We're trying to decide if the difference between a 75 and an 80, is that really due to my treatment, or is this due just to random chance or random error? That's ultimately what we're trying to decide in our particular case. So how do we actually decide if the difference between a 75 and an 80 is really significant or not? We have to plug in our values in this particular case for this particular type of statistic. We have to plug it in to this formula. So in other words, we're going to do 75 minus 80 divided by a standard error. And here I'm going to give you the standard error, and we're going to say the standard error is equal to a value of a 2. So in our particular case, if we take 75 minus 80, which should give us negative 5, so in our particular case, our numerator is negative 5, divide that by a value of a 2, we now find that my z-score is equal to a 2.5. In other words, the difference between a 75 to an 80 based on the standard error is negative 2.5. So in other words, my average of a 75 is 2.5 standard errors below the mean. So we interpret this z-score just as we did with our traditional z-score that we talked about in the previous chapters, that we said, okay, my z-score represents the distance of my score from the mean in terms of standard deviations. Here we just interpret it as the distance of my sample mean to the population mean in terms of standard errors. So here, my sample mean is 2.5 standard deviations below the population average of an 80 in terms of 2 standard errors in this particular case. So now we have to come to a decision, and we have to say to ourselves, okay, this value of a negative 2.5, is that really extreme enough for me to conclude that it is different from 0? So why is it here that I care so much about this 0? Well, if you notice here, there's this huge gap between the null and the alternative. The null hypothesis is very precise in telling me what the difference between my sample mean and the population mean should be. You notice here it tells me that that difference should be equal to 0. On the other hand here, we see that the alternative hypothesis tells me that the difference between my average and the population average just should not be equal to 0. But here, then how different does my value have to be from the population average for me to conclude that it is really different and not just due to random error or just due to random chance? So thus, here you'll notice that I really don't know too much information about the alternative hypothesis. All I know is that my z-score is not supposed to be equal to 0. But then what value is it going to be equal to? What is that value that I would then conclude that the alternative is supported? I don't know. And that's a huge issue that we have in terms of statistical testing. But if you notice here, the null hypothesis is very specific, and it tells me, hey, look, if your z-score is equal to 0, there is no difference between your groups. If your z-score is some other value than 0, then potentially you're not dealing with the null hypothesis. You may potentially be dealing with the alternative hypothesis, and you may potentially be finding differences between your groups. So here, if you take note, the only value that I know in this entire statistical universe of null hypothesis significance testing is the value of 0. Who gives me that? The null hypothesis gives me a value of a 0 because it specifically tells me that my group average minus the population average should be equal to 0, so thus z should be equal to 0, no matter what the standard error is. So here, my group average should be equal to the population average, thus the difference being equal to 0. The alternative tells me it's just not equal to 0, but then what value is it supposed to be? Again, that's an unknown, and I don't like to work with unknowns. I like to work with known values that I can compare my value to. So you'll notice now that Z for the null hypothesis tells me, hey, I have a 0 value. So now in my research study, where I was giving individuals a drug to see if it reduced the number of depression symptoms in a 24-hour period, now using that drug provides me with a z-score of negative 2.5. So now here I can compare my value of z of negative 2.5 to that 0 value and come to a conclusion if there is a difference. So if there is a difference in this particular case between my groups. Okay, so in other words, is there a difference between individuals who receive a drug and who do not receive a drug in this particular case? So that's really the question here that I'm trying to answer. And how am I going to answer that? I'm going to answer that by taking my statistic of z, negative 2.5 in this particular case, and comparing it to my 0 value. So how do we actually go about doing this whole process? So this whole process really begins through what we call null hypothesis significance testing, or NHST. What is null hypothesis significance testing? Null hypothesis significance testing is a method that we use for statistical analyses that allow us to draw conclusions if, for instance, values are different. So in other words, is there a difference between my average and the population average? Is that difference significant or not significant? That's really what we're trying to draw conclusions about. And null hypothesis significance testing provides me with a method of actually doing that. It provides me with this idea or with this technique that will allow me to draw a conclusion to see if the difference between a 75 and an 80 is really extreme or not extreme. That's the purpose of null hypothesis significance testing. How do we achieve it? We do it in 4 steps. Step number 1, we're going to state, the null and alternative in terms of population parameters. Why are we going to identify it in terms of population parameters? Because remember that the null and the alternative talk about the population, and whenever it is that we talk about the population, we always state it in terms of population parameters. We never use statistics because statistics are in reference to samples, not populations. But here, the null and the alternative is the real world. It's out there in the real world. That's the population. So we have to deal with population parameters. Number 2, we're going to collect data. Okay. After you collect data, we're going to calculate stats that are specific to our experiment. So we're going to calculate specific statistics. And why are we calculating statistics? Because again, remember, now we're dealing with a sample. We've randomly selected individuals from the population, and we're now using statistics. So we're not going to calculate all stats that exist out there in the statistical world. We're only using the ones that are relevant to us. So in this particular case, we're using our z-score because that's the one that we calculated in this particular case, right? So our z-score. Step number 3, where we really spend most of the time talking about null hypothesis significance testing, is where we're going to do is we're going to take my statistic of z equaling a negative 2.5, and we're now going to compare it. So we're going to compare my value to the value of a 0. Where does this value of a 0 exist? It exists on this distribution, on this normal distribution, where the mean for that distribution is equal to 0. Why is the average of this distribution equal to 0? Because it assumes that the null hypothesis is true. So in other words, today, if we do the experiment looking at the difference between drug and no drug groups in terms of the number of symptoms in a 24-hour period displayed by depressed individuals, it would assume that the difference between the two groups would be equal to 0. If we do it tomorrow, the difference between the two averages would still be equal to 0. If we do it third day in a row, fourth, fifth, 1,000 days in a row, it always predicts that the difference between those two values would be equal to 0. So the 0 divided by any number would be equal to 0 in that particular case. So thus why the average is equal to 0 in this specific case. Also, remember that the null hypothesis provides me with the reference point. What is that reference point? It's the reference point of a 0, because the alternative hypothesis tells me it's not 0, but then what number should it be? I don't know, right? So here I want to make sure I'm using the correct value as a reference point. In this particular case, it's a value of a 0. So now what I want to do is I want to find on this distribution what we want to call regions of rejection, or what we also call critical regions. What are the regions of rejection or the critical regions? It's going to be that area on a sampling distribution that if my statistic lands within that area, I'm going to reject the null hypothesis. So in other words, here what I'm going to do is I'm going to identify an area where I say if my statistic lands here, I'm going to reject the null. In other words, I'm going to draw the conclusion that the difference between my value and 0 is extreme, so thus the value of a 75 to an 80 is also extreme. Okay, so we're going to tie this all back into our particular example in just a couple of minutes here. So this region of rejection is going to allow me, so allows, there we go, to reject the null hypothesis. So in other words, if my statistic lands in this region of rejection, I'm going to reject the null hypothesis, the statement made by the null. What statement does the null make? No difference, no effect. Okay? So to identify this region of rejection, what do I need? I need what's called a critical value. What is the critical value? It's going to identify the start of the region of rejection, or the critical region. So in other words, this value here, so this critical value, so here, I said critical value, sorry. The critical value is going to help me identify the start of my region of rejection. So why do I need this critical value? Because if you notice here, this is what we're going to call my sampling distribution. So this is the sampling distribution for Z. So the sampling distribution for Z that assumes that the null hypothesis is true. So you'll notice here that this distribution here, this is what we just call a sampling distribution. This distribution here doesn't tell me specifically where my region of rejection is. So where is my region of rejection? I don't know. So what do I need to find my region of rejection? I need my critical value. So in other words, I need to identify the start of the region of rejection, and I do that by finding my critical value. So to find my critical value, what do I need? I need my alpha level. I also need, in most cases, I need my sample size. In our particular case, we don't, but in most cases we will. So for our future discussions of other statistics, we will always be using sample size as an important value to find critical value. And we also need to know the difference between a one versus a two-tailed test. Now, the issue of a one versus two-tailed test, you'll notice here in our sampling distribution that we here have a positive side, which is here, and a negative side. So you'll notice that we have one tail here and one tail here. So we have the option that when we're doing null hypothesis significance testing, because remember, again, I'm trying to find the location of negative 2.5 on here. Okay, so when I find 2.5, negative 2.5, I want to know if it lands in the region of rejection or not. Because if it does land in the region of rejection, I'm going to reject the null. If it doesn't land in the region of rejection, I'm going to retain the null. Okay, very, very important. So here, I have the option of looking in one direction or the other. So I have the choice of looking either to the positive tail or to the negative tail, or I can look to the positive and to the negative. I have that choice. So in other words, if I think to myself, okay, I think my statistic will go to the positive side. Perfect. I can look in this direction here, to the right. If I say to myself, well, I think it may go negative, I can decide to look to the left. Now, if I say to myself, well, I don't know in what direction it's going to go, it may go positive, it may go negative, I can also look in both directions if I want to. So imagine it like driving a car. When you get to a stop sign, you have the choice of looking left, looking right, or looking in both directions. So you say, okay, well, I'm only going to look right. Perfect. There's consequences to only looking right. Well, I'm only going to look left. There's consequences to only looking left. Well, I'm going to look in both directions. Perfect. Now you're playing it safe here in this particular case, but there are consequences with that too. So here in our particular case, we have to use alpha level and that one versus two tail distinction to identify my critical value. What is alpha level? Alpha level is defined as the probability of making a type 1 error. Type 1 error. What is a type 1 error? This is where we incorrectly reject the null hypothesis. So in other words, for whatever the reason may be, we may have incorrectly rejected the null hypothesis. So in other words, let's go back up here to my example of the drug versus non-drug groups. Let's say, for instance, when we randomly sampled from the population of individuals with depression, let's just say that the people that we selected to participate in my study, aside from the drug that we gave them, they also took another drug. So let's say that, for instance, out of the 100 people that we randomly selected, 20 people had taken our drug, but they also took an additional drug that we were not in control of. So they didn't tell us that they were taking another drug. So now all of a sudden, when we calculate all the number of symptoms that they report in a 24-hour period, we notice that they start reporting less and less and less. So here we start looking at that and we start saying to ourselves, wow, look at that. It seems that our drug is working. But in reality, it may be our drug or it may not be our drug either. So it may potentially be the other drug that those 20 individuals took that may have reduced scores enough, so maybe they were outliers, so it drew my average down so far that now it inflates this difference between the two averages, thus making it look like if there really is a difference between the two. So think of it from like a professor's side. Then I say to myself, okay, I'm going to give my students an exam. So what I'm going to do is I'm going to do video lectures. I'm going to have them read the textbook and do homework assignments like we've been doing for class. And let's say, for instance, the true average for the class is supposed to be an 80. Okay, but let's say, for instance, on the day of the exam, let's say that 50% of the class just happened to not have really gotten too much sleep. They were really stressed out about the exam, may not have had their morning coffee, etc., etc., etc. So there are other factors that may have contributed to the scores being lower. So I calculate the average and I find the average to be a 70. And I go, oh, what happened? So apparently my manipulation wasn't strong enough in this particular case. When in reality, it should have been good enough, but there were other factors that I was not in control of. In other words, error, right? This aspect of error that we continue to find all semester long, that is ultimately contributing to the differences in my scores that I'm not in control of. So here, there is this possibility that I may incorrectly reject the null hypothesis, where I may say, you know what? There's a difference between my drug treatment group and the non-drug treatment group, when in reality there should be no difference between them. So here, I'm going to set the probability for making that type 1 error. The maximum that I can set that probability is at 5%. Why 5%? Somebody set that as a standard for us in the behavioral sciences, specifically in psychology, and they decided that 5% was the maximum that we would be able to go in terms of the possibility of us incorrectly rejecting the null hypothesis. It's a very, very conservative value, but there are other disciplines that may want to go higher or even lower as minimum or maximum standards. So here, do always consider that in other disciplines that you may be working in, they may have different standards for alpha level. For us, it's always 5% in psychology, or it's always what we always say, which is 0.05 in this particular case. So in other words, it's just 5% as well, okay? So when we're doing null hypothesis significance testing, I need to have some sheet or something, a table that tells me all my critical values. Luckily, we already have that for our particular purposes for this particular z-score, okay? When we talk about t-test, for instance, in a couple of weeks, that's going to use a different table than the one that we use for z. When we talk about f, it's going to use a different table. When we talk about r, it's going to use a different table. So the unit normal table here that we find in the back of your textbooks that's associated with our z-scores, this is only for z, okay? This is our z-score critical value table, okay? We've used it for probabilities, and now we're using it as our critical value table as well. Okay, so now what we want to do here is we want to find, based on our specific standards that we've set, Okay, so we've set an alpha level at 5%, and we're going to say here that we're going to play this conservative and we're going to go two-tailed. Why? Because I don't know if my stat's going to go positive or negative. Now here, I've already told you what my statistic was, but normally we don't know this until after the fact, until we've already set all our specific conditions for our statistical test. So we always say, well, we're going to use an alpha level of 0.05, we're going to do a two-tailed test, and then we calculate our stat after the fact. Okay, so we never calculate our stat first and then go through and say, okay, well, I'm going to do an alpha level 0.05 and then I'm going to do a one-tailed test. So you always say first, I'm going to do a one-tailed test or a two-tailed test and set my alpha level at 5% or 4% or whatever the case may be. So in our particular case here, we're going to do a two-tailed test and we're going to set our alpha level at 5%. When you go over here to your unit normal table, you're going to find here that we're interested in proportion in the tail. Okay, this is what we're really interested in, proportion in the tail. We're not really interested in proportion in the body or anything else. We're looking at these extreme ends. That's really what I'm interested here, at the extreme ends. Now here, imagine like the distribution that I drew on here, it's also going to be drawn here for us. So in other words, what we're doing here is we have this distribution that has a mean of 0, just as it has here. And what we now want to do is we want to say, okay, what are the extreme endpoints? What are the extreme tails for my specific distribution? Okay, so in our particular case, what I want to do is I want to go and find for proportion in the tail, since I'm interested in a two-tailed test, okay, so I'm interested in a two-tailed test, recall that for alpha level in null hypothesis significance testing assumes that we have the probability of type 1 error set at the maximum. Now, since we're doing a two-tailed test, it's going to assume that alpha level is going to be split. So we're going to split it into two. Why? Because this tail here has to receive of the 5% that we have of a total, right? Because remember, that's my total that I have, 5%. I have to give 2.5% here, and I have to give 2.5% here. Why? So that way, when I add up 2.5% and 2.5%, I have 5%. If I make the mistake and go down in proportion in tail to 0.05, and I use that as a critical value limit for a two-tailed test, in reality what I'm doing is I'm saying this one here has 5%, this one here has 5%. In total, I now have 10%. That's too much, because again, that exceeds my limit of 5%. So what I have to do here, since this is a two-tailed test, I have to just consciously keep it in my attention that I want to find the proportion in the tail that corresponds to each one of these. Because if you do notice, it doesn't tell me here one-tailed or two-tailed. It's assuming that it's a one-tail here. It's always assuming a one-tail. So here, we have to go and find for that one single tail, 2.5% or 0.025. That's the value that I want to go and find in this particular case. So 0.25. So we're going to keep scrolling down until we find 0.25 in terms of my column C. So if you notice here, here's 0.025 right there. And this is associated with 1.96. Now here again, remember our table here doesn't tell you, hey, there's a 1.96 positive and a 1.6 negative. You just have to assume that here. So there's a positive and there's a negative. So now what we're going to do is we're going to go back here to my distribution here, and I'm going to draw, in our particular case, just two lines here. These are arbitrary lines that I'm drawing, but I'm going to assume that they represent negative 1.96 and positive 1.96. So why do I assume that they represent negative and positive 1.96? Because again, with an alpha level set at a maximum of 5%, and here remember, I've gone ahead and split that 5%, right? So in this particular case, let me just go back up here. I've split my 5% to 2.5% on each side. So when I went through and I wanted to find my alpha level associated for 2.5%, I found the proportion in the tail which corresponds to 2.5%. So here 0.025, and that corresponds to a z-value of 1.96 positive and 1.96 negative. So in other words, when I add up 0.025 for the positive side and 0.025 for the negative side, I end up with 5%. So I'm okay, right? I haven't exceeded my limit. So here I've just drawn those lines here to represent negative 1.96 and positive 1.96. So now here I'm just going to change the color of my marker just so that way we can just show the different areas that we're concerned with. All right, so we'll go with blue in this particular case. So now here in our distribution, we now have this area here and we have this area here that represent my regions of rejection. Why do I have two? Because remember here, I decided that it was going to be a two-tailed test. I decided that I want to look in both directions. So now here what I want to do is I want to find the location of negative 2.5. So here again, I just want to change the color of my marker very quickly here. Give me 1 second. We're going to change this into a green color. So here I find here negative 2.5. So I'm going to go find negative 2.5 and I'm going to assume it's going to be right around here. Whoops. Sorry guys. Oops, still didn't work. Sorry, let me just go ahead and make that correction right here. Okay. Give me 1 second, guys. Technical difficulties. There we go. Okay. So here I go and I find negative 2.5. Where did I get negative 2.5 from? Remember, that's the statistic I calculated in my example here. So in other words, I looked at the difference between my average of a 75 and the population average of an 80, divided it by my standard error of a value of a 2, and that gave me a negative 2.5. So now here, I want to now know if negative 2.5 is extremely different from the 0 value. How do I know if it is or isn't? Well, if my statistic lands inside of the region of rejection right here, as it has, I'm going to reject the null hypothesis. So I'm going to reject the null hypothesis. Okay? Why am I going to reject the null hypothesis? Because remember, my regions of rejection allow me to reject the null hypothesis. So thus, I reject the null in this particular case. So we're going to reject the null because my statistic landed inside the region of rejection. If my statistic would have landed anywhere else, so for instance, if my statistic would have landed, and here I'll change the color one more time, in this area here, I would have had to have retained the null hypothesis. Why? Because it would have landed outside of the borders of the region of rejection. So here again, 1.96 is the minimum value that my statistic has to meet. In other words, my statistic that I calculated here, minimum has to meet 1.96 or greater. In this instance, it fell more to the left of negative 1.96, and in this particular case it lands inside the region of rejection, so thus allowing me to reject the null hypothesis. If my statistic would have been a positive 2.5, it would have landed over here, and I still would have rejected the null hypothesis. Why? Because it still would have landed in the region of rejection. Now, aside from this discussion of the null hypothesis. So remember here, if we reject or we retain, in this particular case, since we reject the null hypothesis, what then happens to the alternative hypothesis, right? Because that's the other option that we had. Because remember, we had the null and we had the alternative. The alternative was telling me, look, the difference between the two groups should not be equal to 0. So the z should not be equal to 0. In this particular case, we are now accepting the alternative. So we rejected the null and we accept the alternative. So in other words, I'm accepting that the difference between the two groups is significant. So in other words, going now back up to my example here that I set up. Is the difference between my drug treatment average and the population average significant? And the answer is yes. How did I draw that conclusion? Because again, when I calculated the difference between those two values using my z-test here that I have, giving me a z-value of negative 2.5, I was able to go down into my distribution, identify my regions of rejection based on my alpha level and the number of tails that I'm interested in looking at. And I identify that my statistic of negative 2.5 landed inside the region of rejection, so thus allowing me to reject the null hypothesis, thus allowing me to then conclude that the differences between my average and the population average are extreme, they're not equal to 0, and thus is my hypothesis confirmed? No. So my hypothesis is not confirmed. Why? Because I predicted that there was no difference between the drug and the no treatment group. That's what I predicted, no difference. I'm now concluding that there was a difference based on my statistic. So here, I did not support my prediction, but here, in terms of my research question, is there a difference between them? The answer is yes. So that's ultimately how null hyposignificance testing is really working, that it's answering our research hypothesis and it's answering our question. It's giving me a method for me to be able to test my statistic to identify if the groups differ or do not differ. Now, other issues that we have to concern ourselves with, we have to concern ourselves with the issue of a one-tailed test. Because remember, if we're only looking at one tail, so again, remember, my statistic was negative 2.5. What happens in the case where I say I only want to look at the positive side of the distribution? I don't want to look at the negative side. I only want to look in this direction. Why would we ever want to do this? To be honest, I don't know why we would ever want to do this. We would have to have very strong theoretical justification to do that. So here, what we would normally do is always start off with a two-tailed test, but you can do a one-tailed test if you wanted to. So if you wanted to do a one-tailed test and you want to find your critical value here, now rather than doing a doing your alpha level 0.025, you're going to do your alpha level 0.05, because remember, we only have one tail in this specific example. So here I don't have to split my alpha level to anybody. So here what I'm going to do is in proportion in the tail, I want to go and find 0.05. So here I find the value that's closest to 0.05, which is 0.0495. And that's my critical value is going to be a value of 1.65. Now in this particular case, I said I was only going to look at the positive side, so my critical value of 1.65 becomes positive. So this is my critical value, 1.65 positive. But my z-score was equal to a negative 2.5. So my z-score lands all the way over here, pretty far to the left, right? So this is my z-score in this particular case. So here you'll notice that my statistic should have landed in the region of rejection if I was looking in the opposite direction. So in other words, if I was actually looking on this side, looking at the negative side, rather than the positive side, I would have rejected the null hypothesis, right? Because my statistic would have landed in the region of rejection, right? But here, I'm looking on the wrong side of the distribution. So here, even though my statistic should have landed in the region of rejection, it actually lands in the body. So here, I have to retain the null. Why do I retain the null? Because my statistic failed to land in the region of rejection. Okay, it should have landed over here, or in this particular case, again, if my line should have been all the way on the left-hand side, whoops, let me go ahead and get that line right there. My region of rejection should have began at this line here, and my value should have landed in the region of rejection, but since I was looking in the wrong direction, since I was looking in the wrong direction, I unfortunately have to retain the null hypothesis. So here, since my statistic more than likely should have landed in the region of rejection, but it did not, in this particular case, I'm more than likely making a type 2 error. Why am I making a type 2 error? Because in reality, my statistic should have landed in the region of rejection, but since I was looking in the wrong direction, I failed to miss that true effect. Okay? Now, this brings us to a very important point. Can we then move my tail to the negative side? Absolutely. You can then move it post hoc, right, or after the fact, to the left side and still reject the null hypothesis in this particular case. So here I would no longer then have positive 1.65, but I would have negative 1.65 in this particular case. Now here, this shows us the option of going back one tail versus two tail and kind of what happens to us in this particular case. Now, very important, associated with alpha level and this issue of one versus two tail testing, whenever it is that we go from a one to a two tail test, alpha level decreases per tail. So in other words, when we go from a one-tail test to a two-tail test, my alpha level decreases per tail because remember, I now have to share my my alpha level per each side, right? Because I have a one-tail versus a two-tail test. So now with the two-tail test, I have to give half of the alpha level to one side versus the other. My critical value will get larger and further from zero. Why will it get further from zero? Because here, as now alpha level is decreasing, we're essentially saying, hey, if alpha level is decreasing, I now have to get your statistic to fall into the region of rejection, but it has to be larger. So in other words, if we had stipulated first that my alpha level was 5%, this is the entire side of the distribution that I would have for 5%. But now if we move over to 2.5%, and here let me just change my color very quickly here. If we now go to a two-tail test and thus decreasing my alpha level per tail, because remember I have to now share this 5% with 2.5% and 2.5%, now it's going to push my regions of rejection further. So this is 2.5%. And this is going to be 2.5%. So now in this particular instance, you'll notice that if this is 0 here, the red lines now are further away from 0 than the green line was from 0. Why? Because now it's sharing the 5%, and thus it's saying, look, to land in this area, it's now getting more difficult for you to actually land in this area because this area is now smaller in this particular instance. So this area is now smaller than we had at 5%. So it's much more difficult for us to find power. Remember, a very important term that we've talked about. It's very difficult for us to find power when we do a two-tailed test because my regions of rejection are pushed out even further from 0 because my statistical test of null hypothesis is saying since you're sharing the 5%, 2.5% and 2.5%, I'm now giving you a smaller area to reject the null hypothesis on this side and a smaller area on the other side as well. So thus, again, using the analogy of having a piece of paper and throwing it into a cup versus into the opening for a bottle. The opening for a bottle is very, very small, and your paper is supposed to land inside of the bottle, right? So you shoot, and your paper going with good direction, you have a good manipulation, everything, the paper's supposed to land in there, but since you gave yourself such a small area to allow that paper to go into that hole, now it falls outside. So in that particular instance, whenever it is that we do a two-tailed test, we also have an increase for type 2 error. And why? Because again, we're having this issue that, let's say my statistic was not, so we'll go back up here to our particular example. Let's say that my statistic was a, I'm trying to think of what my statistic would be. 1.75. Let's say what my statistic was a positive 1.75. With a one-tailed test, remember that my critical value was a 1.65, right? So my 1.75 would land in the region of rejection if I was looking at the positive side of the distribution because my statistic is larger than 1.65. But if I do a two-tailed test, now my critical values become 1.96. So now my statistic lands just outside the region of rejection. So it lands just out here. So my statistic was supposed to land in the region of rejection if I would have done a one-tailed test on the positive side of the distribution. But since I did a two-tailed test my um, sharing my alpha level, thus potentially me missing a true effect. So thus potentially leading to type 2 error. Now, this is a brief just summary, a very concise summary associated with doing null hypothesis significance testing. I hope this has answered some of your questions in regards to null hypothesis significance testing. I would recommend looking at this video and then just also looking at part 3 where I begin to introduce the issues associated with power, which are very, very important for our discussions for this coming exam. If you all do have any questions, do let me know, and I'll be happy to answer any of your questions.